A very good morning to all. Myself Dr.A.Mydeen Bibi from Assistant Professor of Mathematics from SFR College for Women, Sivagasi. Today we are going to see about the inverse of matrix from modern algebra. In this session I hope you all going to enjoy. First of all, I want to give some learning objectives of this session. First, I want to define and find a minor and cofactor of an element of the matrix. That should be useful to find the inverse of a matrix. And then we need to find the adjoint of the matrix and also defining and identify the singular and non-singular matrix. The main thing is the finding the inverse of a matrix if it is exist. First of all, I want to define inverse of a matrix. We all know about the 2 cross 2 matrices. I am taking simply 2 cross 2 matrices A equal to A, B, C, D has an inverse if and only if I need to find the determinant. If it is not equal to 0, then only I can find the inverse of a matrix A. Is given by 1 by determinant of A, D minus B minus C A. Such matrices are called non-singular matrices. Let us discuss in detail about the method of finding the inverse of any non-singular matrix of order n. First of all, I want to define determinant. Then only I can find easily inverse of a matrix. We can associate with any n cross n matrix, that is A equal to Aij over a field F, an element over the field F given by the value of determinant is in the usual way and it is denoted by determinant of A. First of all, I want to give a m cross n matrices, that is determinant of A. If A equal to A, B, C, D, then determinant A equal to AD minus BC. If it is not equal to 0, then only we can find the inverse of a matrix. Next, I want to give one small example for finding determinant of A. That is, I am giving A matrices. How we need to find the determinant, I am giving as an example. Next, I want to define singular and non-singular matrix. It's a basic thing, but I want to mention it again. If we are taking a square matrix A is said to be a singular matrix, then the determinant should be equal to 0. If a square matrix A is said to be non-singular matrix, if A not equal to 0. The rule for multiplying two matrices is same as the rule for multiplying two determinants. Hence, if A and B are two n cross n matrix, I am taking one square matrix. I am determining that the product of two matrices, that is the determinant of two matrices is again determinant of A into determinant of B. I want to give a small theorem regarding this. The product of any two non-singular matrices is again a non-singular matrices. I am taking two non-singular matrices A and B. Then if determinant A is not equal to 0 and determinant B is not equal to 0, I am going to find the product of the two non-singular matrices. That is determinant AB equal to determinant A into determinant B, which is also a not equal to 0. Then AB is a non-singular matrix. That is the product of any two non-singular matrices is again a non-singular matrix. Next, I want to give an important definition, that is minor and cofactor. We need to find minor and cofactor to find the inverse of a matrix. First, I want to define minor and cofactor. Let A equal to Aij be the n cross n matrix if we delete the row and the column containing the element Aij, we obtain a square matrix of order n minus 1 and the determinant of the square matrix is called the minor of the element. We denote it as Mij. Next, I want to define cofactor. First, we need to find the minor and then we need to find the cofactor. The minor Mij multiplied by minus 1 to the power of I plus j, ith row and jth column is called the cofactor of the element, that is Aij, and is denoted by capital Aij. I am denoting that Aij equal to minus 1 to the power of I plus j Mij. That is, let A equal to, I am taking one 3 cross 3 matrices corresponding, I am giving one small example for minor and the cofactor. Corresponding the ninth element, that is A 3, 3. We get the 9 minus for this because we are having 3 cross 3 matrices. We are having 9 minus for this. The minor of A11 is M11 How we are going to denote that minor, I am specify here. And also the cofactor of A11 is A11, that is minus 1 to the power of 1 plus 1, that is ith row and jth column, that is 1 plus 1 is 2. M11, that is equal to M11. Next, I want to define about the adjoint of the matrix. Let A equal to Aij be a square matrix. Let Aij denote the cofactor of Aij. The transpose of the matrix Aij is called the adjoint or adjacent of the matrix A and is denoted by adjoint of A. Because I am defining adjoint, that is, if we find the adjoint, then only we can easily derive the inverse of a matrix. Thus, ijth entry of the adjoint of A is Aij. I want to give one special note regarding this adjoint. If A is a square matrix of order n, then adjoint A is also a square matrix of order n. I want to give a small example regarding this adjoint. I'm taking one matrices, 3 cross 3 matrices A. Then we need to find the minors and cofactors of this. I'm giving simple A11 and A12 as a cofactor and minor for this. I need to find the adjoint of this matrices. So similarly, the other cofactors also can be calculated, we get. A into adjoint of A I am deriving here. It is same as the adjoint into A. The properties of adjoint. If I am taking a square matrix of order n, then adjoint of A into A equal to A into adjoint of A is a determinant of A into I. We can derive all those things from this given matrices. So determinant is if it is equal to 0, then it is singular. If it is not equal to 0, then it is non-singular. If it is a non-singular matrix, then only we can find adjoint of A. So I need to give a property for this, that is adjoint of A into A equal to A into adjoint of A, that is determinant of A into I. I want to derive this briefly in detail about that. So I am taking the ijth element of A or into adjoint of A, that is Aij into Ajk. How I am taking that is as a characterization that if I e not equal to j, it should be 0. If it is I equal to j, then it is determinant of A. So A into adjoint must be an n cross n matrices. Wherever we are having I equal to j, that is a diagonal element, we are having a determinant A. So A into adjoint of A is a determinant of A into the identity matrix of diagonal should be 1. So similarly we can find the adjoint of A into A, it is also samely determinant of A into I. Hence I proved this property as adjoint of A into A equal to A into adjoint of A is a determinant A into the identity matrix. Suppose I am taking two matrices. If it is a single matrices, I can derive that A into adjoint of A equal to adjoint of A equal to determinant A into I. If I am taking two matrices A and B, suppose determinant A is not equal to 0. Now consider the matrix B, that is the inverse of the matrix A, that is 1 by determinant A into the adjoint of A. So I am giving a product of these two matrices, that is AB, which is equal to A into 1 by determinant of A into adjoint of A, which is equal to 1 by determinant of A into adjoint of A. It also satisfies the same property of adjoint, that is determinant A by determinant A, which is equal to 1. Similarly, we can prove BA equal to the 1, that is the identity matrix. Therefore, hence if we take a two matrices, then it is also satisfied AB into BA equal to I. Next, I want to define invertible. We know a lot of the definitions regarding in this matrices. I am giving a simply main, whichever it is a main, I am giving the definition here. Let A be a square matrix of order n and A is said to be invertible if there exists a square matrix B of order n such that AB equal to BA equal to I, and B is called the inverse of the matrix A and it is denoted by A inverse. I want to give one observation regarding this, that is a square matrix A of order n is non-singular matrix if and only if A is invertible. I want to give a simple proof regarding this. Suppose A is invertible, then there exists a matrix B such that AB equal to BA equal to I. Hence I want to take a determinant regarding this. It is also the determinant I, that is the identity matrix I, which implies we already know the property, that is determinant of AB equal to the product, that is determinant A into determinant B. So determinant A into determinant B is also the identity matrix I. Hence we need to prove that the determinant A is a non-singular matrix, that is not equal to 0. So that A is non-singular. Conversely, I am taking that let A be a non-singular matrix, and hence determinant A is not equal to 0. Now consider the matrix B, that is an inverse of A, that is 1 by determinant A into adjoint of A, hence AB equal to BA equal to I. So hence A is invertible and B is the inverse of A. We can prove like this. So if it is invertible, if it is an inverse, if it is an conjugate of this, we can take anything, that is A is invertible and B is the inverse of A. It is a very main thing. If a matrix is given, we need to find the inverse of a matrix. We proved lot of properties regarding this, but I need to give the problem solution, how to find the inverse of a matrix. Find the inverse of a matrix. Determinant A equal, if a matrix is square matrix A is given, if a square matrix A is given, since determinant A not equal to 0 and A is a non-singular matrix, hence A inverse exists and it is given by A inverse is equal to adjoint of A and divided by determinant of A. We need to find the adjoint of A first for the 3 cross 3 matrices. That is where Aij, the cofactors, and the minus. First we need to find the minus, and then we need to find the, using that minus, we need to find the cofactors of this matrices. Regarding this, I am having for the 3 cross 3 matrices, I am having 9 cofactors of this matrices. From this cofactors, we need to find the value, and I am finding that adjoint of A. If we find the adjoint of A, we can easily find that we are having the determinant and the adjoint of A. We are easily derived that A inverse is equal to 1 by determinant of A into adjoint of A. So we derive the determinant first and then we derive the adjoint next. So we can find easily the A inverse of A here. I am giving some characterizations of inverse of a matrix. So we already known about the inverse of a matrix. For the inverse of the matrix, we derive some definitions, that is minor, cofactor, and also the invertible. How we use the definitions regarding this characterizations, that is to find the inverse of a matrix, we can easily use minus cofactors and also the adjoint of the characterization. So some of the characterizations of inverse of a matrix I want to mention. So easily we derive the inverse of a matrix. First, I am taking a square matrix A. If it is orthogonal, if and only if, we can find the inverse as A transpose. If a square matrix is given, if the matrix is orthogonal, if and only if A inverse is A transpose. That is, if we can easily find the inverse, that is, we need to write the transpose itself. If the matrices, if the square matrices is orthogonal. So we all know about the orthogonal definition. Suppose A is orthogonal, then A transpose is equal to I know, we know. If I am taking the determinant first, so determinant of A transpose is equal to determinant of I, that is we are getting the identity matrix. So we know the property that the product of two matrices, determinant of the product of two matrices is again the determinant of a single matrices, that is determinant A and determinant of A transpose. So determinant A, we know that A transpose is a determinant of A because A is orthogonal. So determinant A into determinant A is an I, we already know that, that is determinant A is not equal to 0, that is the matrices is non-singular, therefore A inverse exists, we all know that. So we are multiplying both sides with the A inverse, that is A inverse into A transpose is equal to A inverse into the identity matrix, that is A inverse A equal to A inverse. So I am taking that identity matrices into A transpose is equal to A inverse, which implies A transpose is equal to A inverse. We prove the if part easily with the definition of orthogonal. So converse part we need to prove So I am taking the let condition that A transpose is equal to A inverse, that is A transpose is equal to A inverse is equal to I. Similarly, we can prove that A transpose A is equal to I, hence A is orthogonal. So I want to give the one more property regarding this inverse of the matrix. If it is orthogonal, then it is easily transposed, it is easily proved that A inverse is equal to A transpose. It is also that if I am taking a square matrix A, if it is involutory, if and only if A inverse also A transpose. We need to prove it again. So suppose I am taking one square matrix A, if it is involutory, by the definition of involutory, what we know that involutory, that is A squared equal to I, hence I am taking the determinant, that is determinant of A squared equal to I. So I am taking the determinant A squared by the property that product of two determinant matrices is again a product of A and product of B. I am using that property here, that is determinant of A squared equal to determinant of A into determinant of A, which is equal to the identity matrix I, and also the determinant A is not equal to 0. We all know about that determinant A is not equal to 0, and if it is a non-singular matrix, then it is a inverse exist. Again I am saying that suppose A is involutory, A squared equal to I. So here determinant of A squared equal to I am taking the determinant of A squared as determinant of A into determinant of A, which is an identity matrix I. If the given square matrix is not equal to 0 and hence A is non-singular, inverse also exists. So I am multiplying both sides with the inverse. I am taking that determinant of A equal to determinant of A squared, that is A inverse A is equal to A inverse, that is identity into A equal to A inverse, which we proved that A equal to A inverse. Conversely, the if part was proved, I want to prove the converse part. Conversely, let A equal to A inverse, then A squared equal to A minus A into A inverse, which is equal to the identity matrix I, hence A is involutory. I hope you all know about this property. Thank you. I hope this session must be very useful to regarding that to find the inverse of a matrix. Thank you. Thank you once again.